Tonight I'd like to speak mostly about the relation between the two pillars of natural science, elementary particle physics and cosmological physics. The two of them together, as you remember, give us all the laws of, all the fundamental laws of physics on which all the rest of natural science is principle based. And the two subjects have come very close together in the last few years, practically merging, each influencing the other. These exciting phenomena of very small distances and high energy that we've been talking about in connection with elementary particle physics are interconnected with the phenomena of the earliest moments of the universe, phenomena of huge distances characteristic of the universe and its later development as we see it today. Let me begin, though, by reviewing some of the mysteries, some of the things that we were not able to answer about the elementary particle system, some of the things that research workers in theoretical particle physics spend their time on. They would like to know what explains the three families of leptons and quarks. What gives rise to the pattern of masses, to these curious large factors from one family to another, even within the same family. You remember we described a theory of symmetry breaking based on introducing spin zero or spinless bosons, some of which are eaten by the spin 1 bosons when they acquire mass. But that doesn't explain how the spinless bosons are kept from themselves getting very high masses and disappearing from the system. And that's a major puzzle. Is it really true that we have a unified Yang-Mills theory, such as we sketched, one involving effective unification of the enormously high energy, like 10 to the 15th times the rest energy of a neutron or proton, 10 to the 14th times the energy is effectively accessible to today's experiments? Is that a pipe dream, or is it real? We sketched last time a few experiments at low energies that may throw some light on that, but they have not yet done so. If there is a unified Yang-Mills theory, and most theorists in our business think there probably is, what kind of phenomena take place between 100 GeV or so, where the intermediate bosons for the weak interaction are supposed to be found, and this immense energy of 10 to the 15th GeV, where the effective unification is supposed to take place? 10 years ago, when we were first proposing the unified Yang-Mills theory as an idea, it looked as if not much fundamental would happen in between, as if there would be no new fundamental particles and no basically new phenomena between 100 GeV, the mass of the supposed intermediate bosons for weak interaction, and 10 to the 15th GeV, where the effective unification is supposed to take place. And that range, that gigantic range of energies from 10 to the 2 to 10 to the 15th was nicknamed the desert, because it was thought that there would be no fundamental new phenomena in between. Well, this always seemed to me a silly idea. And many of the puzzles that we've described, trying to explain the families, trying to explain the pattern of masses, especially trying to explain the character of the symmetry breaking spinless boson, have led theorists over the last 3 or 4 years to postulate innumerable complicated phenomena occurring between those two limits, 10 to the 2 and 10 to the 15th GeV. So that I have been led to say recently that the desert has been turned by the theoreticians into a jungle. But in fact, nobody knows what goes on. And it's entirely a matter of theoretical speculation, unlike the other material that we discussed earlier, which is essentially right, very well confirmed by experiment. Everything connected with this region between 10 to the 2 and 10 to the 15 is subject of speculation so far, so we get either some firm theoretical advances or some experimental checks. The final question is, does this beautiful generalization of Einstein's theory of gravitation, n = 8 supergravity, which adjoins to the graviton some spin 3/2 particles, and some spin 1 particles, some spin 1/2 particles, and some spin 0 particles. Just what we need to describe the world that we see in our present energies, but not in quite the right numbers and not in quite the right pattern. Does that theory have anything to do with reality? Can we relate it somehow to the phenomena that we think we're observing at the present energy? People are trying all sorts of tricks to relate the content of that theory to the content of what we think we're seeing. The resemblance is so close as to be very tempting. But the lack of an exact correspondence is also very frustrating. And we don't know whether it will be possible to relate that very beautiful theory through observation, but it's a major challenge. I will describe one or two other challenges of present-day theory as we discuss the connection between particle physics and the cosmos. I won't be able to discuss that very thoroughly, but I will just give a few highlights of connections between particle physics and the cosmos. Let's recall a couple of things that we said last time and the time before. You remember that there's an inverse relation in quantum mechanics between mass or energy on one hand and distance on the other. For example, the range of a force mediated by a quantum with a certain rest mass m naught is h bar divided by m naught c. And so in general, as we go to higher and higher masses or energy, we go to smaller and smaller distances. And we are in effect exploring very small distances with a microscope, a sub-microscope, as we go to very, very high energy with our accelerators or our masses of our particles. You remember the orders of magnitude of the energies and distances that we were talking about. The mass of a neutron or proton times c squared gives an energy of 1 GeV approximately, actually a little bit less, about 938.938 in the case of the proton and 0.939 or so in the case of the neutron. The rest energy, rest mass energy of an electron or positron is a half times 10 to the minus 3. The intermediate bosons, you remember, have a rest energy of around 100 GeV, theoretically, and they remain to be discovered experimentally over the next few years. Bulb is gone. Now, who is in charge of bulb replacement?
While you're waiting, could you kill the lights in the front up there? Yeah, can't see.
I'm sorry?
The front row of lights makes it glare on the screen.
Oh. You don't have bulbs with it. Oh, why is that? Well, why haven't you done that? I'm sorry, what is it you want me to do with the lights? Oh, I see, they were causing a glare while the machine was on. Oh, yeah, it's not this bad.
Is it a bulb inside?
It's possible, I will look. Sometimes in the back, there's a... Sometimes in the back there's a door. If you open the door, you can get a spare bulb. Unfortunately, what I want to present today consists almost entirely of these numbers and pictures. They're very difficult to do that. I could do it on the blackboard, perhaps. Yeah, you can get to it, but it's not there. Well, there might be a spare down there. Oh, well, that's a possibility. Let's look into that.
do you recall? What's it from?
Very, very small, around 10 to the minus 8. We'll see why that is in a moment. This maximum is determined not by experiment. The experimental limit is much higher. The maximum is determined by cosmology. Now these energies correspond then to what's called 1 GeV corresponds to around 10 to the minus 14 centimeters. And of course, the 100 GeV for the intermediate boson corresponds to around 10 to the minus 16 centimeters. If we go the other way, we can say that 10 to the minus third GeV, which is around the mass of twice the mass of an electron, that corresponds to a much larger distance. It corresponds to around 10 to the minus 11 centimeters. Multiplying this by 1,000. And 10 to the minus 8 GeV, which could be the mass of a neutrino, be that high. The rest mass of a neutrino. That corresponds to 10 to the 8 centimeters, so 10 to the minus 6. Just to give some orders of magnitude. Now you remember that a typical unification energy for the weak and strong interaction, unified Yang-Mills theory, is of the order of 10 to the 15th. Enormous energy. That would correspond to 10 to the minus 15 times its distance. So 10 to the minus 29 centimeters, which is very small indeed. Finally, we said last time, Planck energy, where quantum gravity becomes strong, is around 2 times 10 to the 19th GeV, even higher. And this corresponds then to around 10 to the minus 33rd centimeter. 10 to the minus 33rd centimeters is a really fundamental length, constructed just out of Planck's constant, the velocity of light, and Newton's constant of gravitation. Just from those three fundamental constants of nature, we get this fundamental length. And when distances get smaller than that, or when time intervals get short compared to this distance divided by the velocity of light, so this divided by c is around a third and 10 to the minus 43rd second. When we get time intervals shorter than this, then we certainly don't know what we're talking about. So we can seriously discuss quantum gravitation. This, for the moment, represents the really ultimate limit of our discussion. But, of course, our ideas may go wrong long before that, many, many factors of 10, before we reach such a distance or such a time interval. Our present physical ideas may go haywire. Now, let's review a little bit the So, what kind of distances do we encounter in more ordinary space? The people of the order of 10 to 2 centimeters. That's about half a person. Then the size of a cell, for example, is the size of around comparable with a micron. It's about 10 to the minus 4 centimeters. So a million times smaller than the length of an adult person. An atom. Now we're getting out of ordinary experience. An atom around 10 to the minus 8 centimeters. And this distance is called Holmström. Something like that. A is a small. And a small nucleus, a light nucleus, is around 10 to the minus 15 centimeters. This distance is called after the microgravity. Right? And from here we go down to smaller and smaller distances. Now, we're going to talk about the cosmos. We should also talk about large distances, starting up from the size of the person instead of down. What happens when we do that? People, again, around 10 to 2 centimeters. What about the diameter of the Earth? That we know, of course, is around 8,000 miles, or about 10 to the 9 centimeters. So about 10 billion times bigger than the What about the diameter of the Sun? That's around 1 million miles, and the 11, the order of 10 to the 11 centimeters. What about the size of the whole solar system, all the way out to the orbit of the most distant planets, Neptune and Pluto? It's also the size of a supergiant star. A supergiant star like Antares, the red star in the constellation Scorpio, you see hanging low over the southern horizon of the sun. Antares has a diameter which is comparable to the size of our whole solar system. And that distance is more like 10 to 13 centimeters. And the distance that light travels in a year is called a light year, of course. Although some journalists seem to think a light year is a unit of time. Politicians, I know, talk about light years. A light year is around 10 to the 18, something like 10 to the 18 centimeters. Now, what if we look at big objects that are large compared with a light year? And interstellar distances in our vicinity, near us, they're of the order of 2 light years, something like 10 to the 19 centimeters. The length of our galaxy, well, different kinds of galaxies have different kinds of tips. Flat, longer than we, considerably longer than we want. The length of the galaxy is around 10 to the 24. Very large compared to what's discovered. This is a very large number. But the remaining numbers, all the way out to the edge of the visible universe, are not so large. The remaining ratios. The size of a rich cluster of galaxies, galaxy 3 times the accessible universe is not all that much bigger. It's just a few times 10 to the 28. Now the masses involved are what? Here, a galaxy has around 10 to the 12 solar masses. The rich cluster has around 10 to the 15 solar masses. And the accessible universe is around 10 to the 21 solar masses. So the big, really big ratio is the one to the galaxy. But there are enough stars in the galaxy, as you can see from this, and enough galaxies in the universe, so that in the accessible universe, there are an awful lot of stars. And since the sun is a relatively common type of star, there are many stars like the sun, very many. And the chances, therefore, that there are planets like ours are very, very low. And since it is not at all clear that there's anything very peculiar about the generation of life, when you have a planet that looks like that, there must be life on very, very, very many planets, very many systems in the accessible universe. So we are not alone. And of course, we have to quote the Walt Kelly's comic strip Pogo. They say, maybe way out there somewhere on another planet, far away in a distant part of the universe, there are creatures more intelligent than we are. Or else, if not, then we are the most intelligent creatures in the universe. Either way, it's a mighty sobering thought. Now, the universe is expanding in a certain sense. Everybody knows that. Objects receding at velocities proportional to the distance out to the edge of the accessible universe with that one number. It's ready. Right? Yes. Yes.
Is it meaningful to ask at this point about these
Oh, can you do that? Can you adjust the lights? Yeah, let me take all these. No, it's all right. It's pretty.
Say a little bit about the concept of accessible versus inaccessible.
Well, the accessible universe is the portion of the universe from which we can get signals. It's possible that in the development of the universe, depending on its structure, we'll discuss that, depending on its curvature, it's possible that the universe has huge volumes that no longer can communicate with us, that are not such that light signals can't reach here from there, or there from here. And the only thing we're interested in for practical astronomers is the region from which we can gather signals. And that's always finite. But the universe as a whole may be either finite or infinite, depending on the curvature, depending on the density of matter. We'll say something about that later. Now, the universe is expanding in a certain sense, namely that the clusters of galaxies, including the cluster in which our galaxy is found, the clusters move away from one another. Oh. The clusters are moving away from one another, but the clusters themselves are not expanding. The galaxy are not expanding. It's something that's often not emphasized in popular descriptions of the expanding universe. We are not expanding. The solar system is not expanding. The galaxy is not expanding. And even clusters of galaxies are not expanding. The universe is expanding in the sense that the clusters are receding from one another. Now, why is that? The reason must be, that all the smaller systems, from clusters of galaxies on down, are bound. And in particular, the clusters of galaxies and the galaxies themselves must be gravitationally bound. In other words, they have enough gravitational attraction to prevent things in them from escaping. Now, that can be true only if, given the motions of the component parts, only if there is enough material inside to exert enough gravitational attraction to hold the things in against their motion. And you can calculate how much that is for each cluster of galaxies or for the galaxy itself. You know roughly from observation what the average motion is of the parts. And so you can figure out how much mass you need in order for gravity to hold the whole thing in and prevent the parts from, or most of the parts, from escaping. Then we observe, with using astronomical methods, how many stars there are, how much mass there is, visible to the various kinds of astronomy, optical astronomy and other kinds of astronomy. We add it up, and we see if that is enough to hold in the material. And it isn't. It fails by a big factor, which is at least 10. So we know from that that astronomy has failed to reveal at least 90% of the material in a galaxy or a cluster. This dark matter, dark only in the sense that it doesn't show up by existing astronomical methods, this dark matter is needed in order to provide the gravitational closure of the galaxy and the cluster. It has to be there. And we don't know what it's made of. Astronomers don't know what it's made of. Particle physics provides a possible answer, not necessarily the right answer, but there is a possible answer which is connected with particle physics that we'll mention in a moment. Now, let me consider the structure of the universe, the geometry of the universe. There are three cases first mentioned by Einstein and elaborated by Friedmann and Lemaitre, who formulated the expanding universe solution of Einstein's equation. Two very interesting people. Friedmann was a Soviet aeronautical engineer, and Lemaitre a Belgian priest. And these two men, not Einstein himself, suggested the expanding universe solution of Einstein's equation, which is undoubtedly the correct one. Einstein had been playing instead with adding another term to the equation, an extra artificial term, to stabilize the universe so it would neither expand nor contract, which obviously it wouldn't with ordinary physics. If you just have a stationary universe, it will fall together by gravity. It won't work. So Einstein added a funny term, which was wrong. And Friedmann and Lemaitre suggested instead that you simply have the universe expanding. In that case, the gravitational attraction slows down the expansion, and everything is okay. Now, in this universe, you can distinguish three cases. One of them, each one is called by many different names, depending on how you look at it, whether you look at it geometrically or you look at it physically and so on. I'll just give the names without explaining exactly how they relate to each other. One of them is called the open universe, or the pseudo-spherical universe. But what it means is very simple. It just means that the universe has so much energy of expansion that it's able to overcome its own gravitational attraction and keep on expanding with enough juice to go on to infinity with lots of energy left over. That's the open universe. The second case, the opposite one, is the so-called closed or spherical or finite universe, in which there is not enough juice to escape the gravitational attraction. In other words, there is so much matter present that the gravitational attraction of all that matter binds the universe together. The universe is gravitationally closed, in other words, like the clusters that we talked about. And it is therefore doomed eventually to turn around and recontract, because it does not have enough energy of expansion to escape its gravitational provide just enough gravitational attraction just to cancel the expansion. And therefore, the universe just barely coasts to infinity, with just barely enough energy to get there. And this case is just on the knife edge between open and closed. It's the only nice case. It's often called the asymptotically flat case. Now, what do we know from observation, from astronomical observation? We know that these two energies, the energy of mass and of motion, and the energy of gravitational attraction, almost balance each other. So we are somewhere near this last case, if not actually in it. Factor of 30 away or so in the direction of being open, if you look at the amount of material that we can see. But we know the amount of material we can see is wrong because of the galaxies and the clusters. And if you say that the whole universe has a similar factor, similar to the one we need for the galaxy and the cluster, then we are very close to this case of just about equal amounts of energy, the case of the asymptotically flat universe, just hovering between open and closed. So to a good approximation, we are in case 3. Now, some astronomers will tell you that they know from the observation of very distant galaxies where we are, that we're on this side of the case 3 or on this side of case 3 or something, but they don't know, they're lying. Because the argument depends not just on their observation, but also on very careful working out of the evolution of galaxies. And they don't know that much about the evolution of galaxies, so they're in fact not really able to say. And for all we know, we are just about in case 3, or if not very, in one of these two cases, but not very far away. I wrote that down. Now, using Einstein's theory of gravitation to describe the universe, and using particle physics, we can work out something about the history of the universe, back to quite early times. But as we go back to very, very early times, the ideas become more and more speculative. And I will try to say something about that. At which times, sizes, temperatures, and so on, the ideas become very speculative, and where they are more considered, at least, to be more reliable. Now, let me remind you, in case you see symbols other than GeV, that GeV is a billion eV. So an EV is a billionth of a GeV, 10 to the minus 9. And an MeV is a million EV, it's 10 to the minus 3rd, in case you happen to see these symbols somewhere. I tried to write everything in GeV, but I may have slipped in one of the others a while. Now, let's review the units of temperature before we go on. Oh, I'm sorry. How do I turn them off? Oh. Is our lighting engineer still here? Can you do something about the lights? Oh, then nobody would be able to take notes. Anybody want that? Jimmy, can you dim them? Is that all right? Yes? All right. Now, before we review the history of the universe, this will be even more rapid than one of those survey history courses where you sneeze and miss a century. Here you sneeze and miss a billion years. Let me say something about temperature. Temperature is proportional to the average excitation energy. So if you're making pairs of things, it's the average total energy. If things are already present and you're just giving them kinetic energy, then it's the average kinetic energy. But anyway, the average excitation energy of the particles or whatever in the size of Fahrenheit degrees. And if we go down to minus 273 degrees below freezing on the Celsius scale, which is 400 and something on the Fahrenheit scale, then that's absolute zero. That corresponds to zero excitation. That's as low as you can go. And so in science, it's conventional to measure things not only in Celsius degrees, but starting from this point, absolute zero, minus 273 degrees Celsius, 273 degrees Celsius below freezing. And degrees measured that way are called degrees Kelvin, after Kelvin, Lord Thomson. And room temperature, which is around 20 degrees Celsius, is therefore about 293 degrees Kelvin, or about roughly 300 degrees Kelvin. Now that corresponds to a particular average energy. Room temperature corresponds to an average energy of motion of the molecules in the air around us of 1/40th of an eV, or 1/40th of a billionth of a GeV. So 1/40th times 10 to the minus 9 GeV. So room temperature can be thought of as about 2.5 times 10 to the minus 11 GeV. It gives you some idea of temperature. This is room temperature on an absolute scale. It's the only thing that makes any sense. Science is to measure temperatures from absolute zero. Now, instead of giving temperature in degrees, therefore, we can directly give it in energy units. It's much simpler, rather than giving it in degrees and then converting it. So I will always give temperature, which is an average excitation energy, in energy units. Most, for purposes like these, scientists will always do that. And you see the room temperature is very, very, very small compared to a GeV, 2.5 times 10 to the minus 11. So now let's look at the universe, the scales of distance, the temperature, the density, at various times back to early times where the arguments become increasingly unreliable. But they probably are pretty good back to very, very early times. Now a lot of details of this are given in that book by Steven Weinberg, which I said sold a lot of copies because people thought it was a sex manual, the first 3 minutes. Now, in that book, a lot more detail is given of the early time. But let me just give a general diagram here with a few highlights in the history of the universe. Now, first of all, there's the present time, which is 10 to the 10th years or so from the beginning, maybe 1.5 times 10 to the 10th, about 15 billion years, somewhere between 10 and 15 billion years from the beginning. The size of the universe, and I'm giving the size of the accessible universe, so I'm not committing myself on the question of whether it's finite or infinite. The size of the accessible universe is always finite. It's, as we said, a few times 10 to the 28 centimeters, or in light years, around 10 to the 10th, something like 10 to the 10th light years. And that's, of course, reasonable, because 10 to the 10th light years for the size corresponds to 10 to the 10th years for the age. The temperature now is around 2.5 times 10 to the minus 13 GeV, so even much smaller than room temperature. It's about 3 degrees Kelvin. And the density is around 10 to the minus 30th grams per centimeter cubed. Very, very small density of matter in the universe today. This energy of the radiation, this temperature, is also the energy, the characteristic energy, of the noise radiation of the photons that have been around since the early times of the universe, which were detected by radio astronomy, and the so-called 3-degree radiation. Now, if we go back to a time when that space-filling electromagnetic radiation, that universal noise, became free, it began to wander freely through the universe. That was a time when the universe was only about 100,000 years, 10 to the 5 years old. So we're going back almost all the age of the universe. When the universe was only 100,000 years old, and its size was about 3 times 10 to the 24 centimeters, that's when that radiation, 3-degree space-filling cosmic noise radiation, escaped. The size of the universe in light years was about 3 million at that time, much smaller than today. The temperature then was higher than it is now, 10 to the minus 9 GeV, much bigger than room temperature. So it's cooled a lot, that radiation has cooled a lot since then. And the density then was only 10 to the minus, was bigger. It was 10 to the minus 19 grams per centimeter cubed. Now, if we go back to when the universe was 300 years old, then the size of the universe was only about 300,000 light years, or 3 times 10 to the 23rd centimeters. That's when the galactic clusters formed as fluctuations in the matter in the universe. The galaxies formed at a somewhat similar time. For our purposes tonight, it's not worth distinguishing probably between the formation of galaxies and the formation of clusters. Astronomers are not clear anyway about how the thing went, whether the clusters were formed and the galaxies developed afterwards or the other way around. The temperature at that time, and this is very important for us to remember, the temperature was about 10 to the minus 8 GeV, considerably higher than room temperature, and is beginning to be of interest to elementary particle physics. Remember, 10 to the minus 8 GeV was one of the numbers we put on the blackboard. So we'll get to that in a moment. The density was huge compared to present density. It was 10 grams per centimeter cubed at that time. What's happened? I'm sorry, I skipped a lot. It's 10 to the minus 15. I'm going to get to the cube density in a moment. 10 to the minus 15, 10 to the 15 times denser than it is now. 10 to the minus 15. No, the huge density is here. Now, the end of Steve's book, the end of the first 3 minutes, 200 seconds or so, found the universe only 30 light years across, the accessible universe, only 30 light years across, and the temperature then was 10 to the minus 4 GeV, and the density was immense. It was 10 grams per centimeter cubed. And that's when light nuclei were formed, like the helium nucleus, the alpha particle. And in other words, matter was more or less in the form then that it could be cooked by the stars to form all the heavy nuclei and everything that we know today. You know that the heavier nuclei were all cooked in the stars, subsequently. But the light nuclei were already formed by that time, by the end of the first 200 seconds. Yes?
Yes. Can you say that the universe is 200 seconds old?
Yes.
Having the size of 30 light years and particles or whatever travel faster than that to get out there?
What's travel faster than light?
The particles of the universe. It's 30 light years.
The accessible universe was 30 light years across. At any one point,
Yeah.
no.
Velocity of light still constant then?
Yeah.
Big star is a point.
Question is, how do you see something 30 years ago in a universe 200 seconds old?
All right, that's something crazy.
Particles out there, or that's where the curvature happens?
No, no, we're talking about two different kinds of measures of distance or time, which are roughly coincident here in the universes, in the modern universe. But as we go back, the scales get increasingly out of whack with each other. What we're measuring here is the proper time, so-called, the time experienced at a given point. Light years away, which also went back only 200 seconds, had obviously been out of communication with this thing at one time. And as you go back, this problem gets more and more acute. And so, while it's perfectly possible to have these distances and these times, what is mysterious is how the different parts of the universe knew that they ought to be similar to one another. When if you trace each pair back far enough, that pair of points were out of communication with each other. Could not have light signals pass between. That's called the horizon, because they were beyond, one was beyond the horizon, the other, beyond the light horizon, the other, out of accessible. Each point, if you follow it far, if you take 2 points and you follow them far enough back, each one goes out of the accessible universe of the other one. They pass out of each other's horizon, beyond each other's horizon. And that problem is illuminated by this increasing discrepancy between these small Now that horizon problem is a major difficulty of cosmology, which just in the last few months has possibly been solved by an ingenious suggestion, which I will describe. In fact, I described it the first night in answer to a question, but I think not many people followed it. I will try to describe it some more tonight. Now let's go back a little bit further. If we go back to 1/100th of a second in the proper time life of the universe, when the accessibility distance was something like 1/3 of a light year, the temperature was 100th of a GeV. The density was 10 to the 9th grams per centimeter cubed. That's when neutrons and protons and neutrinos and antineutrinos and electrons and positrons began to decouple and no longer had to be in equilibrium with each other, but could come off and exist on their own without having to be constantly interconverted. In other words, it was at this time that the neutrons came out and no longer had to be in constant interaction with the protons, giving back and taking electrons and neutrinos and so forth. That was at about this time. Now if we go back still further to 10 to the minus 4th to 10 to the minus 7th seconds, depending on the details of the calculation, when the size of the accessible universe was 10 to the 15th to 10 to the 16th centimeters, and the temperature was 1/10 of a GeV to a GeV. The density was something like 10 to the 19th grams per centimeter cubed. At this very, very short time, when the accessible universe was quite small, that's when the baryons began to separate from each other. Before that, they were jammed together so tight, it was so dense, we follow it further back, that the baryons were touching, and therefore the quarks could move around freely from one to another, and therefore there were no baryons. It was just a big quark soup. And before this point, the confinement was done by the universe. The universe was confining the quarks. And so they could move around freely within the universe because their density was such that the baryons were all touching and were penetrating one another. So it's around this time, between 10 to the minus 7th and 10 to the minus 4th seconds, that the neutrons and protons emerge as distinct entities from the quark soup which prevails before that time. Now, before that, things become very unreliable. Now, of course, they're unreliable already here in the sense that we have very little evidence for most of this. But this is a straightforward computation using known particle physics and known laws of gravitation, known thermodynamics, and so on. In other words, some new physics would have to have intervened in between to spoil this. This is based on extrapolation from things that we know perfectly well, assuming that these things were true back then. Of course, they might not have been. But this is the simplest thing. The simplest thing to believe is that this is essentially right. It doesn't represent the introduction of any highly speculative physical ideas. Now, if we extrapolate back further than that, then, of course, things are much more doubtful. With extrapolation to a time earlier than 10 to the minus 4th or 10 to the minus 7th or whatever it is seconds, represents the use of ideas which are themselves speculative. Not only are they speculative because they're being used in cosmology, but they're speculative in themselves. For example, we go back to 10 to the minus 11th seconds, things are still fairly straightforward. That's when that corresponds to a temperature which is the mass of the weak interaction intermediate boson. And so that's when the weak interaction became weak. Before that, effectively, it was strong. Because the temperature was so high that the intermediate bosons could be produced and destroyed by the temperature. So this is still fairly reliable. But we could go back much further. For example, to 10 to the minus 36 seconds, when the accessible universe was only a centimeter. And the temperature was 10 to the 15th GeV, the energy of unification. And we can say that around then is when, according to the theory I will describe in a moment, matter began to predominate over antimatter. The density was 10 to the 79 in CGS units. The furthest any reasonable person would want to go back at all, even for speculative purposes, would be to the time corresponding to the Planck length. We wrote it up there, 10 to the minus 43, 10 to the minus 44 seconds. If this makes any sense, the temperature would have been 10 to the 19th GeV, and the density 10 to the 95th. But this is fantastically speculative and hardly worth talking about at all. Now this whole page may be altered by the idea that I described a moment ago, which I'm going to talk about, the new idea. So this page is not only very speculative, but recent ideas may invalidate it completely. However, it's worth mentioning because many people have talked about that. Simple extrapolation. Now, before we go on to the early moments of the universe and the new ideas about it, let's review some important ideas of common interest to elementary particle physics and cosmology. There are a whole series of such ideas. Let's go over them one by one. These will not be terribly unfamiliar because the particle physics involved in each case is something we've discussed. So here we're reaping the fruits of our discussion of particle physics in the last 3 sessions, and we're able to apply some of what we learned to the problems of the universe and of astrophysics. You remember that unified Yang-Mills theory suggests that there may be little rest masses for the neutrinos. Experiment sets rather high limits on those rest masses. But I mentioned that cosmology sets lower limits, and we'll see why. If the neutrinos have rest masses, in particular, people think maybe the tau neutrino might be the heaviest one, so it might be the important one. If it has a rest mass as large as 10 eV, that is 10 to the minus 8 GeV, the number that I kept writing, then that results in, if we study the history of the universe, in neutrinos being the principal constituents of galaxies and clusters. There would then be more mass of the galaxy and more mass of a cluster of galaxies in a neutrino fog hanging over the galaxy or the cluster than there would be in the regular stars and clouds and so on that we can detect by astronomy. In other words, the dark matter would be accounted for. 10 or 20 times the mass of the visible stuff in a galaxy or a cluster would be there in the form of slow neutrinos hovering over the galaxy. Now, if there's no rest mass, you can't have slow neutrinos. They travel with the velocity of light, and the whole thing is out of the question. But if the neutrino has a little tiny rest mass, of the order of 10 to the minus 8 GeV, then you would get precisely the right dark matter from the neutrino. And cosmologists reluctantly accepted this after some years of hesitation. And finally, they say that actually would be an ideal way to account for the dark matter. It needn't be right. It's just a possibility. But it does work perfectly. So that if the neutrinos do turn out to have masses in this range, something like 10 to the minus 8 GeV, then they would be the principal dark matter in the galaxies and in the clusters. And in fact, the usual matter would be only 10% or less. And the galaxy should be thought of in that case as primarily a clump of neutrinos with some other stuff in there as well, stars and clouds and so on, but mainly neutrinos. Very interesting switch on the usual way of looking at galaxies and clusters. Now, let me re-emphasize that this is not necessarily true, but it is a possible way to account for the dark matter. If the neutrinos do turn out to have that little rest mass, then it is. Now, remember something else that we said when we listed the temperatures and so on in the history of the universe. Let me recall that. We said that back when the galactic clusters were formed as fluctuations, when the universe was 300 years old only, and the size of the accessible universe was 300,000 light years, at that time the temperature was about 10 to the minus 8 GeV. Isn't that interesting? In other words, when the clusters were formed, the temperature was just the temperature of this hypothetical mass of the neutrino. And therefore, not only could the neutrinos be the primary constituents of galaxies and clusters, but the galaxies and clusters might have been formed as fluctuations just around just because of the neutrino, because the temperature was then roughly equal to their rest mass. So it provides a possible explanation not only for the dark matter, but for the very existence of galaxies and clusters. But let me emphasize once more that this is not necessarily true. It's just a possibility. It's a possible connection between cosmology and particle physics if the neutrinos do turn out to have those rest masses. They may not. They may have zero rest mass. In this case, that explanation fail. Now, another connection between neutrinos and astrophysics, not unconnected with the one we just mentioned. I talked about this a little bit in answer to questions, but I never presented it formally, I think, as part of the talk. For years, the Davis experiment has been going on in the Homestake mine, gold mine in Lee, South Dakota, looking for neutrinos from the sun in a carload of cleaning fluid. And as we said in answer to questions the last few times, the result is too low for theory. For years they couldn't see any. Now they say maybe they do see some, but not more than a quarter of what the lowest theoretical prediction is. Now, why is that? Well, various explanations can be put forward. The simplest is that the experiment's wrong, because it's only one experiment, and nobody's checked it. It's a very difficult experiment, and there's only one chemist in the world who knows how to look for one atom in a carload of cleaning fluid. That's Mr. Davis. So they can't check it very easily anywhere else. One ruthless but brilliant physicist suggested that somebody should bring an extremely radioactive source down into the mine without telling the mine workers or the Homestake company or the physicists, and see whether the neutrinos from that very strong radioactive source would set off the equipment. That would be one way of testing it. Well, needless to say, that wasn't done. Another experiment is gradually being prepared using a different substance, which tests a different portion of the neutrino spectrum. And that should help a lot, because for that portion of the neutrino spectrum, the theory of the sun is not really in question. You can calculate very reliably how many neutrinos there should be in that portion of the spectrum. That may work better. Otherwise, one can always imagine that there's something the matter with the theory of the sun. Now, of course, they've exploited all the uncertainties in the theory of the sun, all the ones that the theoretical astrophysicists admit exist. And there may be other uncertainties that they don't admit exist. And so maybe the theory is wrong. My colleague, Willie Fowler at Caltech, suggested some years ago a different explanation, which I think I mentioned the first night. And that is that the sun went out. It isn't shining anymore. Now, if that happened in the center, where the nuclear reactions are going on, it would take 1 million years for the news to reach the surface. The neutrinos would shut off immediately, because they come directly from the nuclear reactions in the middle, and the sun is transparent to neutrinos, they just come right out. So the neutrinos would be absent. The sun would keep shining for 1 million years, though, because the news wouldn't percolate to the surface until 1 million years had gone by. Then it would go out also in the electromagnetic spectrum, and then we'd have a very serious energy crisis. That theory is not widely accepted. Another possibility is that there's some particle physics effect that's taking place. And this, again, is just very speculative. It's not necessarily true. It's just an idea. And may be wrong. May easily be wrong. But you remember we said that if the neutrinos have little masses, then along with the little masses, they will also get probabilities of interconversion from one type to another in flight. So that if the neutrinos have these little masses, which they may have, then also an electron neutrino can be converted in flight into a muon neutrino or a tau neutrino, and then those will be converted back, and you'll have oscillating waves of character of the neutrino. They will oscillate from electron neutrinos into muon neutrinos into tau neutrinos back to electron neutrinos, and so on, as they pass through space. Now, that would lead, then, to a reasonable factor of suppression of the solar electron neutrinos, because they come out of the sun as electron neutrinos, and in between the sun and the Earth, they would get partially interconverted to other things, which wouldn't show up in the Davis experiment, because the Davis experiment tests only for electron neutrinos. So a modest factor of suppression could be accounted for that way, if indeed there are these, not only neutrino masses, but these interconversion probabilities for the different kinds of neutrinos. Again, this is speculation, and nobody knows if it's true. Now, another very fundamental point has to do, I think I mentioned that once also in answer to a question, but let me now present it formally as part of the talk. That has to do with how matter came to predominate over antimatter. In the list of epochs of the universe, I pointed out the time when that probably happened. And I discussed the mechanism once in answer to a question, but let me now discuss it in a little more detail. And it didn't arouse much interest at the time. But much the same argument was revived about 10 years later with more detail by a lot of other people in this country. And it's since been accepted as a very likely explanation of why the universe, as far as we can see it, doesn't seem to have much antimatter, but mostly matter. The idea is that in the very early moments of the universe, there were equal amounts of matter and antimatter. But then, early on, at the time, at the epoch that I mentioned when we looked at the list of epochs, matter began to predominate through the following mechanism. It requires three essential features. One of them is very easy to arrange, and that is that the universe be out of thermodynamic equilibrium in the early moments. Well, that's very easy to arrange. There's no doubt that's the case. The second thing, indeed, as pointed out by Sakharov, is the violation of CP symmetry. You remember, that's the symmetry under which we exchange particles and antiparticles, and left and right. But we do not exchange forward and backward time. And we know since 1964, from that brilliant experiment of Fitch and Cronin, which won them the Swedish award a couple of years ago, that in fact the CP symmetry is violated. So there is a symmetry between matter, an asymmetry between matter and antimatter. And if you couple that with the non-equilibrium character of the early universe, and with one other thing, then you can get this predominance of matter over antimatter. Now, what is the one other thing? The one other thing is that you must be able to create and destroy protons, baryons. But that is just the thing that happens in the unified Yang-Mills theory, although that was not known to Sakharov in 1967, when he suggested that baryons might possibly be created and destroyed. It was thought then that the laws of physics would require them to be conserved, and he suggested that that might be false. But with unified Yang-Mills theory, we have a reason to believe that maybe baryons can be created or destroyed. Maybe the proton decays, as we said, possibly at a rate of about 10 to the minus 32 per year. They're looking for it now all over the world in mines and tunnels, and may see it within a year or so, perhaps, if we're lucky. And if you combine that idea with the CP violation, matter-antimatter asymmetry, and with the non-equilibrium character of the early universe, then you get a prediction that the universe would in fact become, in the early moments, asymmetrical between matter and antimatter. We haven't worked out the sign so as to be able to predict whether it's matter or antimatter. But in principle you could. If you knew enough, you could actually predict which one would predominate. You have to know certain pieces of experimental information. And you could predict which one would predominate. But there's a very brilliant idea which may explain, in fact, why the universe shows in our neighborhood this extreme predominance of matter over antimatter. So there's no sign, in fact, of an appreciable amount of antimatter. This was a mystery for a very long time. For many years, people were unable to relate the experimental CP violation to this macroscopic effect in the universe. The crucial thing is the proton decay, baryon non-conservation. Now, another couple of phenomena that we can describe, again, we mentioned them in answer to questions, but let's talk about them now in the discussion, proper discussion itself. Einsteinian gravitation distinguishes itself from ordinary Newtonian gravitation that we learn in grade school, but principally when the gravitational fields are very strong. When gravitational fields are weak, you might as well use Newton's theory. The difference is very small. But in the presence of strong gravitational fields, then it makes a lot of difference. Or when the speeds come very close to the velocity of light. And the most dramatic example of that is a black hole. You remember we pointed out that a star running out of fuel may collapse to a white dwarf in which the atoms touch. Or if conditions are right, on running out of fuel, it may collapse to a neutron star, only a mile across, in which the nuclei are touching. And those have been observed in many examples as pulsars, with beacons rotating for unknown reasons. But if the mass is right, and the star runs out completely out of fuel, it can collapse physical reality in the 1930s by Oppenheimer and Snyder. They pointed out that a sufficiently heavy star actually would collapse. It wasn't just a possibility. It actually would collapse to a black hole. And since then, astronomers have wondered whether they couldn't detect a black hole. And remember that it distinguishes itself from a white dwarf or a neutron star in that the collapse doesn't just occur to the point where atoms touch, as in a white dwarf, or to the point where the nuclei are touching, that's 10 to the 15th density in a neutron star. In the black hole, the collapse is complete. The collapse just keeps on going. The reason is that in Einsteinian gravitation, all energy gravitates, including the energy of gravitational attraction, also gravitates, feeds on itself, and therefore keeps on collapsing faster and faster, more and more, and the whole system falls into a point. Well, anything that falls in is gone. Those signals can emerge from inside the so-called Schwarzschild radius. The Schwarzschild radius is actually outside the black hole. The material has fallen in practically to a point, but there is a distance outside, a radius, within which nothing can send a signal out, because the gravitational field has just become so strong in there that it pulls light back into the black hole. Can't escape. But it's important to realize that the Schwarzschild radius, within which that happens, is outside the material of the black hole, far outside, because the material is actually falling practically into a point. So no information can come out of that black hole except the mass. If it has an electric charge, I suppose you can see that too, the Coulomb force. A couple of other macroscopic parameters like that. But essentially, only the mass can be detected outside. No other kind of property or signal can come out. The gravitational pull continues, however. The thing continues to exert gravitational pull, and from that size of that gravitational pull, you can determine the mass of the black hole. Because of that gravitational pull, the black hole is sucking in material. And if a star is nearby, material from the star can be sucked in, will emit X-rays as it falls in, which are death cries as the material is disappearing into the maw of the black hole. And we can observe those X-rays, hearing essentially the cries of help from the material falling in from the nearby star. And this is the way astronomers believe that they are detecting indirectly one or two black holes today. One of the suspected black holes is in the constellation Cygnus, the Swan, the Northern Cross, visible high up in the summer sky. In there, there's an X-ray source where the structure seems to be, as in this picture. The whole system is rotating. There's a star and a mysterious thing rotating around each other. Material is being sucked out of the star, falling into this mysterious thing, and emitting X-rays. And the very strong suspicion is that the mysterious thing is a black hole. You can measure its mass from the gravitational properties of the double system. And it seems to have the right mass to be a black hole. And it's considered likely that the material is being sucked out. The X-rays are coming out of the material falling into the Schwarzschild radius. The Schwarzschild radius is out here, and the cries are emitted as the stuff disappears into the Schwarzschild radius. Beyond that, you can't hear anything or see anything. These are visual cries, X-rays, just by the acceleration of the stuff down here. Here's the Schwarzschild radius. Another thing we mentioned about a black hole is Stephen Hawking's previous suggestion of a mechanism by which a black hole can lose some of its mass, some of its gravitational pull, some of its energy. It used to be thought that black holes were permanently of the same mass, except for capturing additional mass. That they could only grow, in other words, by capturing additional mass from things falling in, but that they couldn't lose mass. But Hawking pointed out that through a quantum mechanical effect, they can also lose mass. A quantum fluctuation out near the Schwarzschild radius creates a pair, for example, that energy is lost to the black hole. Well, sometimes it is. In that case, nothing happens. But when the pair is made at the Schwarzschild radius, one outside and one inside the Schwarzschild radius, then the one outside goes away, the one inside falls in. And in that way, Hawking showed, energy is gained by the electron and positron comes out, and therefore lost by the black hole. So the black hole gradually loses energy by the quantum mechanical process of pair creation in the vicinity of the Schwarzschild radius. Classically, of course, the electron and positron would have to be made at a point. Quantum mechanically, you can make them kind of apart, and you can get this effect. Now, there are also other phenomena, very conspicuous phenomena in the universe, that may be connected with the black holes, or may not. We don't know. They are very, very bright sources of optical, radio, or other kinds of electromagnetic radiation. Very bright, very tiny, star-like. Very tiny compared to the distance between stars, and rapidly fluctuating. These things occur in many different places. They occur in the centers of galaxies, and they occur far out in the universe, where they are so bright and so distant that you couldn't see a galaxy if it were around this bright object. And so you don't know whether there's a galaxy around it or not, but you suspect there may be. These most brilliant objects of this kind, which radiate 10 to the 47th ergs per second of energy, 10 to the power that they radiate is 10 to the 47th ergs per second at the brightest. They are quasars, or quasi-stellar sources. So they have a brightness, for the brightest one, of up to 100 trillion suns, even though they're tiny, not much bigger than stars, and fluctuating rapidly. And now there's a whole there's a whole range of brightnesses of such objects. Not all of them are called quasars. The brightest ones are called quasars. Then there are dimmer ones, where you can see the galaxies around them because you don't see them far enough away anymore to be able for the galaxies to be invisible. Those are called N-type galaxies or Seyfert galaxies, and so on and so forth, down from 10 to the 47th ergs per second down to something like 10 to the 38th ergs per second, or 100,000 suns. At that level, we see one inside our own galaxy. In the center of the nucleus of our own galaxy, infrared detectors, such as the ones at Caltech, see a tiny, fluctuating, rather bright source in the infrared. It probably radiates another frequency too, but it's detected in the infrared. 10 to the 38th ergs per second, or thereabouts, may be related to these much brighter sources at much greater distances, possibly. So even our own galaxy may have a junior version of such a bright, small, fluctuating object at its very center. Now, what are these things? Nobody knows what they are. Nobody has any idea. However, there are some speculations. One speculation is that each of these objects has a very heavy black hole inside, and that the radiation is caused by things falling into that black hole. That's a possibility. In other words, it's conceivable that a quasar is connected with a black hole, like a black hole in the middle. Stuff is falling into it and sending out this very bright, this very important signal. And this little thing in the center of our own galaxy might also have a black hole attached to it, sucking in material. This is only one theory. It may not be right. I mention it because it's a very interesting possible speculation about the nature of these bright objects, including quasars. So we deal with it one. We might be able to do it if we saw something orbiting around it. It's not inconceivable. The mass of a black hole is a physically accessible quantity. No. You don't think of it in connection with the universe. Think of it in connection with its local by Caltech infrared astronomers and other infrared astronomers. It's too bad that it's so hard to see it in the center of the galaxy. There's an awful lot going on in there. Otherwise, you could get more information about this very bright point in the middle. Now, one more important remark about the universe. This is perhaps the most important of all, and something that has been proposed very, very recently, just in the last couple of years, and in its most satisfactory form just in the last few weeks. So let me introduce the problem. Again, I mentioned this once in answer to a question, but that wasn't the real question. I didn't present it properly. The average density of matter in the vacuum is not necessarily zero in quantum field theory. Quantum field theory can have a virtual production of pairs and things in the vacuum, and the energy of the vacuum is not obviously zero. You like to define the energy of the vacuum to be zero, and that's what quantum field theorists did for a long time. They would calculate the energy of the vacuum, and it would come out to be non-zero, in fact, infinite usually. And then they would say, well, but that doesn't matter. Everybody knows the vacuum has zero energy, and we'll call it zero. We'll subtract the energy that we find in the vacuum in our field theory. Subtract it out and call the energy of the vacuum zero. And for most purposes, in quantum field theory, that's a perfectly good thing to do. But it has been pointed out that Einstein's gravitation is watching us all the time. And we'll notice that vacuum energy. And when we subtract it away, we're not fooling gravity. Gravity will see it. And therefore, we must arrange that the vacuum energy really be zero. Or else gravity will take account of it, and there will be an extra term in Einstein's gravitation theory because of this energy. It's called the cosmological term. Now we know now from the behavior of the universe as revealed by astronomy that this cosmological term is not there. Or at least it's very, very small. In natural units coming from the gravity constant, Planck's constant, and the velocity of light. In these natural units, that cosmological constant, which is proportional to the energy of the vacuum, is less than 10 to the minus 120. So if we say it's a more than 1, that's the biggest error yet in physics. By a factor of 10 to the 120th, which is even big for astrophysics. Although errors tend to be large in astrophysics. In fact, throwing around factors of 10 to the 10th or 10 to the 20th is not uncommon in theoretical astrophysics and cosmology. This was emphasized by the marvelous Russian-American physicist Gell-Mann, who wrote a number of popular books, 1, 2, 3, Infinity, and various other things. He was a hard-drinking giant of a Russian family. I never knew him. And he used to love to play practical jokes. Particularly when he wrote letters to scientific journals, he loved to play practical jokes. He had a student named Alfred, Dr. Richard Alfred. And when Alfred and Gamow wrote a paper together, they put Hans Bethe's name in the middle. So it would be Alfred Bethe Gamow, without asking Bethe. Another time, though, to emphasize how astrophysicists often lose big factors, he wrote a letter to the Physical Review and deliberately made a mistake in the letter and wrote an erratum. But he didn't send in the erratum, of course, until the letter had been printed. When it had been printed, then he sent in the erratum saying he had made a mistake. He had been planning to do that all along. The erratum said, in my letter, Physical Review, page so-and-so, I unfortunately made an error in equation number 4 by a factor of 10 to the 27. This does not affect the result. But a factor of 10 to the 120 is noticeable, even in cosmology. So we must explain somehow this zero value, or nearly zero value, of the cosmological constant, and nobody knows how to explain it. N=8 supergravity, or indeed any of the supergravity theories, helps a little bit. It gets rid of many sources of this vacuum energy, or cosmological constant, but it does not, at least so far, abolish it. So we don't know the answer to this problem. Many of us are working on it, trying to explain this mystery, and there's all sorts of complicated ramifications, which I will not discuss. But briefly, the situation is that we don't understand it. We don't know why it's zero, or very nearly zero. However, a very interesting remark has been made in connection with this. Although we don't know why it's zero, or nearly zero, maybe it wasn't always zero. Maybe in the very, very early moments of the universe, in the first fraction of a second of the universe, it was different from zero. This could be, because it depends on the conditions in the elementary particle physics, quantum field theory, vacuum problem. And in the very early moments of the universe, at high temperatures and so on, the vacuum could have been different. There could have been a phase transition, for example, from one kind of vacuum to another at the high temperatures occurring in the early moments of the universe. And therefore, the vacuum energy, zero now for some unknown reason, might have been non-zero and very big in the very earliest fraction of a second of the universe. This idea was suggested in a not very satisfactory form by some young American theoreticians about 3 years ago. It was also looked at in the Soviet Union. And recently, the Soviet man, Vinde, has come up with a new version of this theory, which looks very much more satisfactory than the previous attempt. And in this new version, it actually works. You assume that elementary particle physics is set up such that in the very, very earliest fraction of a second of the universe, there was a non-zero, very large cosmological constant, which then changed as a result of a phase transition to a lower value, which for some reason is zero. And that we still don't understand why the new value is zero. But that the old value was different is an idea that seems to work. If so, it completely modifies the history of the first tiny fraction of a second of the universe. Not the first page that I showed you, that's unchanged. But the second page, the highly speculative one, gets completely altered by this idea. What happens is that the universe would explode suddenly in the very earliest moments and be diluted by a factor of 10 to the 10,000 in radius, or in separation of things, or 10 to the 30,000 in density, over a very short period of time, in a tiny fraction of a second. Now, why is this of any use? Well, it would completely rewrite the early moments of the universe, the history of the early moments. But what good would it do? Well, it would explain the following 7 mysterious things. 6 or 7, many. I'm not sure if I've given them all. It would explain why the universe is nearly in balance between the gravitational energy of attraction and the mass and kinetic energy of expansion. You remember we said that these two are very closely in balance, not more out of balance than a factor of 10, and maybe in fact just about equal. That intermediate case between open and closed. Well, why is that true? These two energies could be out of balance by a factor of 10 to the 50th, for all we know. Why should they be so close? Well, that's explained by this picture. Because this dilution by this gigantic factor makes the universe asymptotically flat and makes these two things equal. Next, you remember the horizon paradox that some of you noticed. It's very difficult to see why, when the proper time age of the universe was so much smaller than the size of the accessible universe, why the universe should have known that the various parts should all come out of the same place. How could they possibly know that? Well, it wasn't true, is the answer. In the very earliest moments of the universe, there was a sudden expansion by this factor of 10 to the 30,000 or whatever. And our data are therefore all wrong for the very earliest moments of the universe. In the earliest moments of the universe, the size and the time could have been consonant with one another. Next, it explains why the universe exhibits an approximate homogeneity and why it exhibits an approximate isotropy, that is to say, similarity in different directions. Again, the reason is that it may have had a lot of irregularities, but they were sure ironed out when it suddenly expanded by a factor of 10 to the 30,000, something like that, in the early moments. All of these irregularities would have been appreciably ironed out by that correction. A more complicated problem, which I can't explain, but which it does help with, is the problem of how the CP violation, which we measure at very low temperature, could have been effective in making matter predominate over antimatter at a time in the universe at a very high temperature. Because we don't know that that CP violation survived at very high temperatures. All we know from our laboratory experiments is that it exists at zero temperature. And most theories of it find it very difficult to make it persist up to very high temperatures. But it turns out in a complicated way that this idea also helps with that problem. Another problem it helps with, which is difficult to describe, but I'll mention it. In unified Yang-Mills theories, there are very peculiar objects which mathematicians would call solitons, little stable globs of energy, and which resemble single magnetic poles of electromagnetic theory, which are normally not thought to exist in electromagnetic theory, but which in gigantic masses and energies do sort of exist in unified Yang-Mills theory. These monopoles caused tremendous trouble with the early history of the cosmos, if the early history of the cosmos is as usually extrapolated. But in this inflationary universe, it's not a problem. And in fact, that's what it was invented for 2 years ago. It was invented to solve this one little problem. It turned out to solve many, many, many problems. So it's a possible idea. Again, it's not known to be true. It's just a speculation. But it's a very interesting speculation, and one well worth remembering. And so let's recall that the page that we described, in which we described the earliest moments of the universe, this one, may have to be torn up. All of these very early times, before this, these early times, all this has to be changed if we have the explosive or inflationary universe for the first little bit of time. The other page, though, can still be around. That's this one. The one that goes back to a fraction of a second or so, the forms. This represents simply the application of known physics back to a time when known physics could have been practiced. So although nobody can verify this today, there's no reason to believe there's anything wrong with it. But the earlier history of the universe may have to be totally rewritten if this inflationary or explosive scenario should turn out to be around. Not completely. It has to be changed, the parameters have changed, the time has changed, but the idea is not changed. In fact, it's helped. Because the CP violation no longer has to hold up to such high temperatures in the inflationary universe. And so that idea, although the detailed arithmetic is totally different, that idea is preserved and works even better than it did before. So the idea that matter predominates over antimatter for the reasons alleged by Sakharov is still a perfectly live idea, even in the presence of the inflationary universe. So let me end then simply with this question as to whether all these bold speculations will be, in fact, justified, or at least some of them justified. All of these represent enormous extrapolations in energy. Remember extrapolations by factors of 10 to the 14th or more in energy in our fundamental theories of physics, and they represent enormous extrapolations